time.
Okay, so here's what we had. Alright, and we know it is kind of dim for these 4 bulbs. And we also know we can break the circuit like that. Okay? Alright, parallel. Yeah! Look at that.
Those are really bright.
Okay? Super bright, alright? But I'm using the same electrical outlet. What's the voltage here?
120.
120. Okay. I'm using the same 4 resistors. If I measure them with the multimeter, I get the same resistance for each one. Okay? But they're brighter. Okay? There is more current, but how come I can get more current and use the same bulbs?
Resistors.
But they're the same resistors. Okay, also check this out. Yeah. Yeah. Okay. They are independent of each other. Okay, one goes out, the other ones can still stay on. Okay, that's parallel circuit. Okay, so let's flip over to the other side. And here's a diagram. Alright, here's the positive side of the battery. Here's the negative side. Okay, and we know that current is the flow of positive charge. Okay, so we've got that. And at this point right here, what's going to happen to the currents? They're all going to start splitting up. Okay? Over here, there's only one path for the current to follow. There's no branching. There's no dividing. Okay? The same 4 resistors as I had on the other diagram. And we're still going to draw an equivalent circuit. Okay? So let's do that. We're going to simplify it into one battery, some wire, and we are going to make it one resistor. Okay, now you guys already told me, oh, the current's got to go up. Okay, why else would it be this bright if the current didn't go up? And you're right, the current did go up. Okay, if the current's going to go up, what has to happen to the resistance in the circuit?
Let's go down.
It's got to go down. Okay, but I'm using the same resistor, so why is it going down? Okay, and you can kind of think of it, it's not a perfect analogy, you can kind of think of it like a highway. Okay, see how I have 1, 2, 3, 4 lanes here for the traffic to go through? Okay, it's like a 4-lane highway. On the other side, how many lanes do I have? It's a 1-lane highway, right? Series circuit is one single loop. Okay, now it's not a perfect analogy because how many lanes do I have right here? One. Okay, so the traffic analogy, it kind of helps, but it's not a perfect analogy. Okay, so adding branches simply gives the current more places to go. Okay, and if I keep adding bulbs to this circuit, then I'm going to give more and more places for the current to go.
So it'll be brighter.
Okay, it will get brighter every single time. Alright, so I got 4 bulbs here. How about we do 5, 6, 7, 8, 9, 10, 11, 12 bulbs, wire them all in parallel like this, and plug that in. Good idea?
Sure. Until it exceeds the limit in the break.
Okay, there's limits of things. The current can get way too high, and you can start blowing up light bulbs, and you can start flipping breakers. Okay? You can do the same thing at your house by plugging in too many things to the same home circuit. Because your houses are wired in
series.
Parallel.
Close.
Okay? Alright? All wired up in parallel. Okay? Now, but that's good. If your house was wired in series, okay, check it out. Here's all of your things at your house. Oh, look. You turn your toaster off, everything goes off. Okay? That's not good. We don't want it like that, right?
Definitely in series.
You have to have everything on at once.
You'd have to have everything on at once. Okay, here's your refrigerator.
So if you unscrew like 3 of those, that last one's not going to be very bright?
Well, brightness is actually going to stay the same.
Wow.
Okay?
Why would
This,
adding more-
because you're going to see in a second with the rules, but this is getting 120 volts. This is getting 120, this is getting 120, and this is getting 120.
Why would they get brighter than if you added more? Wouldn't they just get 120? They wouldn't get brighter if you added more.
Good plug space.
I thought you said that.
Okay, so if we start adding more to the circuit,
Yeah. The current would go up to match.
the current in the wires would go up, okay? But the brightness of each bulb is not gonna, well, that's a good question.
Well, because it's like matching the voltage for every light bulb that you add, right? It's like just enough current increases.
I'll have to think about that a little bit, I'm not sure. That's a good question. What will happen for sure is there'll be a lot of current in this part of the circuit, okay? And this part of the circuit will melt down, right? Yeah, we're gonna get melted wires because there's gonna be too much heat in here, okay? And these are gonna get brighter and brighter and brighter. All right, so here's your refrigerator, here's your kitchen light, here's your toaster, here's your microwave. Okay, can I have them all on at once?
Yeah.
Yeah, okay, that's probably not a problem. All right, if I turn one of them off, they all stay on. Okay, so your refrigerator still runs even though your kitchen light bulb's off, right? That's a good thing. We got to wire stuff in parallel. Okay, now sometimes we'll wire a switch on one of these wires that is in series with this within a parallel. It's a series within a parallel, man.
So you can turn, like, if you have like 4 lights on your fan, like all 4 of them out.
Yeah,
Or
yeah, exactly. Okay, so we can put some series within parallel sometimes. Okay, today you guys are working on junior varsity circuits. That would be an example of a varsity circuit, a series within a parallel. Okay, both at the same time. All right, we'll get to those too. Okay, so the resistance of the circuit, okay, is kind of confusing. Adding branches decreases resistance. Okay, and when I say that, I mean the overall resistance of the whole circuit. Okay, so don't put this on your paper, but if I go over here and I add a branch like that, okay, my overall resistance actually went down for the circuit. Okay, and even more current's going to flow. So if I start hooking too much stuff up, that's when I can throw a circuit breaker at my house. Okay, have you guys ever thrown a circuit breaker?
Yeah.
Okay,
Yeah.
what did you have plugged in? Lots of stuff. Okay, if you take a shop vac, a circular saw, and a table saw and try and run them all at the same time, you'll probably throw a circuit breaker. Okay, unless your circuit's wired up for that kind of amperage. Right? But that's a protection so you don't burn down your house.
Like fuses.
Okay, they used to be fuses, now they're switches. Because fuses would actually burn out, then you gotta take it out and buy a new fuse and put it in, kind of like a light bulb. Alright, and your car still has that. Okay, your car's got those little fuses in there. Okay, so to use the rules, here's how we're going to get this equivalent resistance. We're going to say 1 over R equivalent is equal to 1 over R1 plus all these inverse values. So we got all these fractions. Okay, so for the example circuit right here, find the R equivalent. Oh, dot, 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 meaning as many resistors as we have.
You want that?
Find the R equivalent for the example circuit. Everybody needs a calculator.
I have a question. So, I have an exterior light on my car, and it runs from the batteries to a switch,
Yep.
and then the switch has like, and then it runs to the light, and then back down, get back into the negative.
Back to the negative.
So then, when I have the switch off, does power run through the wires anyway?
Nope,
No?
nothing happens.
Okay.
Because the circuit has to be a complete loop.
Okay.
Okay. Okay, let's see what you guys got. Okay, alright Melanie, what'd you get?
0.54.
Okay, point what?
0.54.
Very close. You might have mistyped a key. It sounds like you did it right, you just, it's close to that, okay? Alright, now how many of you guys got 2.0 something something?
Yeah.
Okay, you guys need to do one more step. 2.0, is it 2.08 or
Yeah.
something?
Yeah.
Okay, you're almost there. You need to do one more thing though. Here's what you found.
Oh.
Okay.
So divide that by 1.
Yeah, you found 1 over the answer. So now we need to do 1 over that.
Wait, what?
So it's 0.48.
Oh.
So it's, we just did 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4.
Yep.
And then
1
all
plus a
over-
half plus a third plus a fourth is 2.083.
Oh, okay. And then
Okay.
we divide it again.
Yeah, and then you do, because see how I'm solving for a variable in the bottom of a fraction? I need to get it out the bottom of that fraction by multiplying it over here, okay? And then I would be doing 1 over that. Or a simple way to think about it algebraically is if I flip this fraction, what do I have to do over here? Flip that fraction, and then it's going to give me the right answer. Okay, just flip both fractions. Okay, all right, any questions? Okay, so this is still a 6-volt battery. This is 0.48 ohms. Okay. And let's look at this. Okay, on this side, I had a 6-volt, but I had 10 ohms of resistance. Okay, so 10 ohms here, and then I only got half an ohm here. So the resistance went down by a factor of 20. The series circuit has 20 times the resistance of the parallel, in this case. Okay? Yeah, it is a lot. Okay, because this resistance went down so much, the current went up. Alright, so current right here, let's say this, it divides at branches. Okay, and divides proportional to the resistors. Okay, so you guys have heard path of least resistance, right? So which of these is going to get the most current?
First one. 1 ohm.
The 1 ohm, right? Because it's the path of least resistance. Now it doesn't get all of the current. Some of that current's still going to go through the 4 ohm. Okay? Some of it's still going to go through the 3 ohm, but the 1 ohm is going to be our highest current. Okay? So how do we calculate it? Let's get the total current first. So we can say I total is equal to V total over R total. Alright, and that's just going to be our 6 over our 0.48.
Did you say that our battery is 6 volts still?
Yep, yeah, I just made it the same voltage battery. Okay, so if you do that, you're going to get 12.5. And you can see the current went up a bunch from the other side. Okay, now that's not on your page. Okay, so let's begin filling out our chart. Our overall resistance, 0.48, 12.5 amps, 6 volts.
What about your ohms?
Yep, we know those two. Okay, and now we need to get the current and voltage of each one. But before we do, let's check and see if physics actually works. Okay, what's the resistance of one of these bulbs? You guys remember?
They're like 1.56.
Okay, let's go to ohms
Yo.
and test one. Okay, so this one happens to be between 32 and 34. Let's say 32 ohms. Okay? Alright, so for our circuit, calculate it real quick. You don't have to write it down, but calculate the resistance of this whole circuit.
Did you say 32 or 3.2?
32. So I'm going to do a 30-second, plus a 30-second, plus a 30-second, plus a 30-second,
32 times 4.
or a 30-second times 4. And then I'm going to have to inverse that number. Okay, so what do we get there, Jesse? 8. Okay, that sounds right to me. Do you guys agree?
Why do you have to inverse it?
Yeah.
Because, again, you'd be getting 1 over REQ if you didn't inverse it.
Oh.
Okay? So you've got to inverse the answer.
Wait.
Okay, so let's connect wires here to the plug and see what we get. Whoa, it's jumping all over the place.
Too high. Is it too high again?
No, I don't think so. Maybe my multimeter's running out of batteries or something. Okay, oh, here we go, look at that. I just needed a good connection. Okay, so we got 8.6, 8 or 9 ohms. Physics actually works, I'm not making this stuff up. It's amazing. Okay, that's one of the things I love about physics is it's real world application. Okay, all this math that you guys are learning how to deal with, all right, we can prove it by doing demos and experiments. Okay, all right, any questions so far on parallel?
How did you get 8 from 128?
Yeah.
Oh, yeah, I'll get that. All right.
Okay, so it's not 128.
Oh, you said 32 times 4.
No, a 32nd times 4.
8 what?
So let's look at this. It's 1 over 32
Why is it 1 over 32? Where is 32?
times 4.
Where
Okay,
is
so
32
all right.
is the resistance.
Okay,
of
let's
the
lay it
single
out on a
bulb.
piece of paper.
32 is the resistance of the single bulb.
Okay, it's the same circuit as this right here, but each resistor is how many ohms? When I measured one light bulb, how many ohms was it?
32.
32. Okay, so it's the same circuit diagram except all of these are 32. So to get our total, I got to do a 30-second plus a 30-second See what I'm saying?
So that's where we just ignore the, like, 1, 2, 3, 4.
Yeah, the 1, 2, 3, 4 is just for that other example. Okay? So, if I take out my calculator, somebody stole my favorite calculator.
Let me borrow it.
Okay, I do 1 divided by 32 times 4, and I get 0.125. Okay, so that means 1 over RT equals 0.125. Okay,
How many have to divide?
so then I got to do 1 divided by 0.125, and I get 8.
That makes sense.
Okay, you guys see? Alright, cool. Good. Alright, so it should be 8 ohms, and it actually works out. Okay, so the current's going to divide. Alright, we know that this one's going to get the most current. Okay, but how do we find the current? Let's look at our chart. Okay, to get I, what do I need to know? The easiest way to do it is to get the voltage for each resistor. Okay, so what we're going to do is we're going to do this rule first. Okay, then we'll go back and get the currents. Okay, so voltage for parallel, very easy because it's the same for each branch. Okay, same for each branch. All right, let's look at this. Okay, you guys been to Waterworld before?
Hayward toaster.
Okay. They got water slides at Waterworld. Alright, you guys been on the white slides that go like this? You guys are
Yes.
very quiet today. Okay, there's 3 different slides. They all start up here, they all end down here, same elevation. Okay, one of those slides goes like this. Whee! Okay, the other one goes like this, and then there's one that goes something like that. Okay, probably not quite that steep of a drop. Alright, just go with it, okay?
Backwards.
You like hit your face on it.
Okay, now do you guys see how they all have the same elevation loss?
Yeah.
Okay? They're all losing the same elevation, they're all starting and ending at the same place. Okay? But they're different paths. Okay? This over here, this parallel circuit's doing the same thing, but instead of gravitational potential, oh look at this. I got a battery.
Bam.
Okay? That battery's going to drive the charge. Instead of water, I've got charge flowing. Okay? Now, let's put resistors here instead of water slides. Okay? Do you guys see how they are all involved with the same voltage loss here? Or not voltage loss, but voltage drop, as it is said in electronics. Okay, that's a parallel circuit, and they're kind of parallel branches. So, each branch here on our diagram is going to get the total voltage of 6 volts.
So
Okay.
6 divided by 4.
So we can say that's V total, okay, or battery. Is equal to V1 is equal to V2 is equal to V3, and so on for as many resistors as I add. Okay? And we said earlier that each of these bulbs here is getting 120. It's getting the full voltage of the wall. Here, they had to split up that 120. Okay, so 120 divided by 4 for each bulb. Okay? So we can go here, and it makes this chart very easy. 6 volts, all the way on down the line. Okay? And that makes the currents really easy, because current is equal to voltage over resistance. And now we know each, so calculate all those voltages. Okay?
So if you took your series, like you got rid of 3 of the light bulbs on there, completely got rid of them in the system, Then the one light bulb would get 6 volts and it'd be just as bright as the other
Yeah,
ones.
so if I got rid of these three and wanted just this bulb,
Like
it would
lock
look
it
like
off
those.
in the background.
Yeah, because these three are affecting this bulb too. These make it independent.
Okay.
Okay, so here we're doing 6/2, 3 amps, 2 amps, 1.5 amps. Okay, so let's go up here and we can say I equals V over R applies to each resistor.
Where is it the same?
Okay, and last thing, let's put down here P equals IV. I'm not going to do that because I know you guys know how to multiply. I'll let you do that on your own. Okay, you can calculate all the wattages. Okay, and those all come out in watts. Okay, any questions on parallel circuits?